All right, hello everybody. Is that on? There we go. Okay, so today I have the privilege to introduce our colleague, Scott Parker. Scott's a theorist with expertise in fusion energy science. He recently served on the DOE Fusion Energy Sciences Advisory Committee and the D3D National Fusion Facility Program Advisory Committee, and is also a fellow of the American Physical Society, so he's definitely the right guy to give this talk. His research focuses on multi-scale kinetic simulation methods and extreme-scale computing applied to tokamak, edge turbulence, and energy transport. Some major issues in magnetically confined fusion. He's also working on problems in quantum information science, so I think that's actually just because it's required by law of all faculty members at CU.
All plasma physics is quantum information.
That's right. We're recategorizing it to get some more money. But in his case, it's relevant to fusion plasma science in that it includes impact of quantum computing on nonlinear computational mathematics and direct numerical simulations of ultra-cold ion crystals, which is, adjacent to plasma physics. Has some striking similarities in some aspects, at least in terms of the techniques, I would say. Scott could probably say better. He received his PhD in engineering science from UC Berkeley and his BS in nuclear engineering and also BS in mathematics from University of Wisconsin-Madison. He was a staff physicist at Princeton Plasma Physics Laboratory, PPPL, for 6 years, and then has been a faculty member here at CU since 1996. And he is a great colleague and friend. So Scott, please tell us why fusion is still 30 years away and has been for the last 70, 75 years. Thanks.
Thank you, Mike, and thank you all for this opportunity to tell you about some of the exciting things that are happening in fusion energy. It should be quantum information. Quantum computing is always 30 years away. That's what it should say, actually. But no, that's an old joke I often hear as I wait for the elevator. Fusion is 30 years away, and it always will be. And the reason that's funny is because it's true to some extent. And but there's a lot of exciting things going on right now in fusion, and I hope to share some of that with you. Okay, here's my outline. Let me begin by just introducing what fusion energy is. It's the energy of the sun and the stars. In the sun's huge. There's the gravitational force is 38 times what it is on Earth. And so you can fuse hydrogen, what's known as the proton-proton chain. But in a reactor on Earth that's a meter or so in size, you have room temperature at the edge, say at the wall. You have 100 million degrees in the core of the reactor. It's impossible to achieve this with protons interacting. So use the DT fusion reaction, which has a much higher cross section. And DT, deuterium tritium, and DT this reaction produces an alpha particle and a neutron, a 14 MeV neutron. So recently, there's been a lot in the news about fusion. If you pay attention, you've probably seen some of these stories coming from various media sources. And what's really happened is that there's been an enormous amount of private investment in fusion, on the order of $6 billion since 2021. And this has generated a lot of development of experiments by private companies. So these are startup companies mainly. And so there's been an enormous flurry of activity that wasn't there previously. And if you look at the funding for fusion, now the left of this column is the US DOE, but they're really the only US national organization that funds fusion publicly, and it's on the order of $0.7 billion, and it's been pretty stable. It increases slowly. It had a slight bump up recently. There was some actually funding, $50 million for funding private companies. The last cycle But what's changed radically is the private funding. And I'm getting these numbers from the Fusion Industry Association. They are big numbers, but they're just ballpark numbers. But right around 2021, all of a sudden you see there's a big jump. And prior to 2021, there was some private research. Lockheed Martin had a Skunk Works project. They still do. And there was a company called Tri-Alpha Energy in Irvine, California, that had some research. That company started in 1998. But then the startups began. And there's over 40 of these companies. There's a few large ones, and I'm going to talk about the largest ones. But why was there this big change? And it's the, it's climate change is what's going on here. And the big tech companies are taking this seriously, and they're setting goals of being net neutral or net zero carbon emission, or just zero carbon emission, maybe not net zero carbon, depends on the company. But all the Magnificent Seven, minus Tesla and NVIDIA, have all pledged to hit these goals. And President Biden has said net neutral by 2050. But this has also just changed the climate in investing. So investors want sustainability. They want zero carbon. They want to see social justice issues cared for. And this matters now when you try to get funding or your company. And in fact, ExxonMobil was ranked in the top 10 for the ESG rating. That's the sustainability and social justice rating. And Tesla wasn't on the list, and this angered Elon Musk to no extent, and there was a Twitter storm. So if you look at there's a lot of firms out there. There's a lot of high net wealth individuals behind these funding groups, and they're focused on sustainability and social justice. And it's sort of the big tech, or tech can solve all the world's problems mantra type of thing. And people really believe that tech can solve the world's problems, and they're investing money. And also they think this will help. They'll make money by doing so, by solving the world's problems. It's all good. There's also the Inflation Reduction Act. So there's been enormous investment by the federal government. Not all that money, those hundreds of billions of dollars, have not been appropriated, but they're big numbers. And in 2022, the green energy startups were funded at about $50 billion. That's a lot of money. And Fusion was $2 billion of that, so it's a small piece, but it's significant. Now, as the interest rates go up, the money disappears, and so we'll see what happens. Money's not free anymore. Venture capital is not talked about as much as it was in 2021, 2022, but these startups continue. And if the four big ones, Commonwealth Fusion, which is a partnership with MIT, is the biggest. It has about $2 billion. It's backed by Bill Gates. There's a company in Vancouver, Washington, backed by Jeff Bezos, called General Fusion. And I'll talk a little bit about these things. TA Technologies, I mentioned, is Google is heavily involved. Helion Energy is backed by Sam Altman of ChatGPT fame, and they're very ambitious. They say electrical power by 2024 and commercial power by 2030. I mean, this is in the news. This is what they're saying, both the CEO and Sam Altman. These numbers that I'm throwing around here, there's a lot of numbers. I've done some research, but it's hard. It really comes from press releases. Okay, so the accuracy, it just gives you an order of magnitude estimate. So there's a lot behind just the press release. There's the agreement details, the period of commitment, things like that. And so these numbers just give you a ballpark of what's going on out there. So the four big ones, are shown here. There's one more big one called ZAP, but it's not as big as these. So Commonwealth Fusion is doing a conventional tokamak, more or less, but their secret sauce is a very high magnetic field, and I'll talk about that. They're using high temperature superconductors. These are not room temperature. They're 20 Kelvin to 77 Kelvin, boiling point of nitrogen superconductors. It's called Rebco ribbon or tape, rare earth, barium, copper oxide, and it also can be in a braided. It can also be braided, but it's very robust, and you can get very high fields, 12 Tesla. And a conventional tokamak gets 4 or 5 Tesla, so that's a big boost. We'll see the fusion power scales as b to the 4th. So that's what's going on there. That's very exciting, and that's in the suburbs of Boston. General Fusion is backed by Bezos, and it's liquid walls that are compressed with pistons, and they're currently using lead, but they'll go to lithium so they can breed tritium, and they compress a field reverse configuration, which is sort of a self-organized plasma. Actually, Tobin had one of these in Duane not too many years ago, and we'll talk more about that. Now they want to smash a spherical tokamak, but that's a recent development and a whole nother topic. And so that compression will heat the plasma and hope for fusion. I don't know if it's really going to work, to be honest. To be polite. TA Technologies, they are taking two of these self-organized plasmas, FRCs, which I'll talk about. There's a picture of one. They're smashing them together. They're merging them in the center, and then they're blasting it with high-energy neutral beams. And one of the successes of the fusion program is producing a lot of neutral beam power to heat tokamaks, and they're taking this technology and applying it to a different type of plasma. Helion, backed by Sam Altman. I know Google has been very interested in TAE. Helion is again taking 2 FRCs and they're merging them, and then they're compressing them with a strong magnetic field. And so that's what's going on. Those are the big companies. I'm now going to switch in parallel this other very exciting development, and that's the recent ignition results on the National Ignition Facility. Okay, so the National Ignition Facility, we call it NIF, was constructed. It's been going on for 20 years. It started operating in 2008 with not great results, but over time they've achieved a quite remarkable result, and which I'll talk about. The ICF program is funded by DOE at about the same level that the Fusion Energy Sciences program is funded. It's a big program, and their purpose is not to produce economical fusion energy. Their purpose is to develop data that's used for thermonuclear weapon design and stewardship. Will the bomb still work after it sticks around for a long time? So this data that they collect, I can give you an example. I don't have a Q clearance, so I can tell you. They will measure the equation of state for a high energy density material, and then that will go into a hydrodynamics code where they can model an explosion. And so that's very useful, because in the Clinton era we banned underground testing of thermonuclear weapons, and so this is a sneaky way to get around that fact by doing it with the numerical simulation. Now, One more thing is, so this is at Livermore, and we have and Yuan Shi is from Livermore. He works in ICF. He does magnetized ICF, which is a unique spin on the ICF problem for energy purposes and economical energy purposes. But anyway, he's works in the ICF program, so I should mention that. So December 5th in 2022, they achieved the goal of the program, which is remarkable. And so they had 2 megajoules on target, and they got a burning plasma ignition, and they got out 3.15 megajoules. And then later in the summer, they got about a gain of 2. Okay, so that's the goal of the project. So it's an enormous success, and it's the first time we've ever gotten thermonuclear ignition or burning plasma in an experiment. So this is very exciting. And the picture here is the NIF target chamber. All right. So how does that work? Well, using indirect drive. So there's a huge building with tons of lasers in it. That's all I know. And there's 192 laser beams, and they impinge on a can with 2 holes at the top and the bottom, and the laser beams go into the can. This can is called a holoram. It's made out of high-Z material, depleted uranium and gold, and it radiates like crazy X-rays. And those X-rays are what heat and compress the capsule in the center, okay? And the reason the holoram's a good thing is that it provides sort of a uniform bath of very intense X-rays, whereas if you do direct drive directly with the lasers, try to hit a pellet, it's not as nicely symmetric. Yeah.
Real quickly, size scale for
Yeah, it's like the pellets. Oh, what's going on here? Yeah, so the capsule's about is a couple micrometers, or a couple millimeters in size, in diameter. There's the size scale, and the hologram in that picture is drawn to scale. And so this is a PRL, and in this case, they got a burn, but they did not get net gain. The gain was less than 1. It was about 0.7 in 2022. But what I love about this is that all the details are given. It's all published, so you can kind of get an idea of what's going on here. And what's shown is the on-target laser power here in terawatts as a function of time. So over a few nanoseconds, they blast the hologram walls. It radiates X-rays, and that compresses the pellet. And I'll talk a little bit about how that happens. This is a cryogenically cooled pellet. It's capsule. It's a spherical capsule. It's cryogenically cooled. There's deuterium, tritium ice here. There's deuterium, tritium gas. And then there's this high-density carbon material on the surface. So this is really a scientific art. Target design is very complex. And coming up with the best thing to achieve fusion is, the best target to achieve fusion is very complicated. And science and a lot of knowledge, experimental knowledge. But the high density carbon material, that is like an amorphous carbon that's deposited using chemical vapor deposition, and it has to all be very smooth. Everything is perfectly symmetric. If there's any asymmetries, this drives instabilities. And then the fuel mixes with the ablator. Okay, so the HDC, high density carbon, is what we call an ablator, and the X-rays come in, they heat up the ablator, it ablates, and you get plasma blowing off of this high density carbon ablator, and it acts like a thrust, rocket thrust, that just smashes the pellet, smashes the capsule. Pellet capsule. I'm having troubles today calling it a capsule. I don't know exactly why. But so it has to be perfectly symmetric, and why is that? Well, there are Rayleigh-Taylor-like instabilities. This is where, and if there's any sort of asymmetry, spherical asymmetry, these Rayleigh-Taylor instabilities will grow, and they will mix the ablator material with the fuel and quench the burn. And the Rayleigh-Taylor instability, just showing it here, is where you have a high density fluid over a low density fluid. This is in force balance or pressure balance. So, if there was a smooth membrane here that maintained the surface, everything, there would be no exponential growth. However, if you take this situation, which is in force balance, and you perturb it slightly, so this is that fuzz here, it will go unstable and the two fluids will mix, which is shown here. And you get mixing, and you get the mushroom shape here of this, which is characteristic of a Rayleigh-Taylor instability. So when the ablator material is accelerating into the fuel, initially the light fluid is the plasma, and the heavy fluid is the ablator, the HDC. And so I've drawn effective G's there. It's not really G. It's just the acceleration of the material itself. Now, later, as the capsule compresses, it begins to deaccelerate. It compresses the DT fuel. It deaccelerates, and at that point, then the DT fuel is the light fluid, and the ablator, the high-density carbon, is the heavy fluid. Either way, there's this instability, and if this is not perfectly symmetric, the ablator material will mix with the DT fuel and quench the burn. And what I'm showing here is from a Livermore fluid code, okay, computational fluid dynamics. It's compressible fluids, so compressible hydrodynamics is actually hard to do on a computer, but it can be done. And the red is the high-density fluid, and the gray is the low-density fluid that's compressed. And you see the mixing occurring here, the mushroom shape of the Rayleigh-Taylor instability. And this picture is very pretty. And the purpose of this picture actually was to show the accuracy of the code. Because if you start with a particular azimuthal perturbation, it grows exponentially, and you maintain that symmetry. And that's what that was the purpose of this figure. So in reality, it's more like the peach fuzz situation where you'd have lots of unstable modes initialized. Yes?
So this Rayleigh-Taylor instability problem was apparently solved in the early 50s in hydrogen bombs. So why is it such a big problem here, and it's fixable in a bomb?
Well, the bomb, you just have an enormous amount of I don't know. I'm not allowed to know. Neither are you. But there you have an enormous amount of power from your nuclear explosion to compress things. So you have an enormous amount of power input. So you can just solve it with a sledgehammer, right? No, that's a good question. I don't know. All right, so Sure, Joe.
How do you get spherical symmetry if you start with cylinder layers? Is it the X-ray field?
It's the X-ray field. It's this like bath of X-rays.
And
Just
symmetrically, even though they're coming from a cylinder, they end up having spherical symmetry.
yeah, I assume the idea is that it's essentially a uniform bath of very high energy X-rays. It's sort of the goal in that. Now, okay, but they would like the program would like to get past that and eventually do direct drive. And this is an active area of research at the Rochester laser facility, because there you get better efficiency. You don't have this intermediate hull around. But yeah, the goal is to get a sort of a uniform bath of very high energy X-rays. I love the question. That's good. It means you're awake. All right. So there's a lot of challenges with fusion, with inertial confinement fusion. One is that the electrical energy that you need is 100 times the energy on target with the lasers. So lasers just are not electrically efficient, and this is a real problem. I'd say it's sort of a fixable problem, which I'll mention later. Okay, so the rep rate, the lasers have to recover. It takes about a day at best, and if you did one pulse a day, you'd get about the power of a light bulb. If you were able to speed that up, an incandescent bulb. If you were able to speed that up to about 2 a second, you get the power of about 100 megawatts, which is a significant amount of power, but it's still small. I mean, a nuclear power plant generates about 3,000 megawatts thermal, so much more than that, or even a coal plant. Okay, but there are some things in the future coming. One is direct drive that we were just talking about. If you can couple to the fuel, to the capsule much more efficiently if direct drive would work. This would be in the future, and then also using heavy ion beams as a driver. So you can accelerate heavy ion beams very efficiently, electrically efficient, and so heavy ion beams could replace the lasers as a driver once direct drive is working and you understand how to design a good pellet and get all the symmetry, get a perfect spherical symmetry and all that. Then maybe you could consider consider heavy ion beams. Yes.
So this 2.5 megajoules of output energy, is that in the form of kinetic energy?
Well, there's a split. There's alpha particles. There's 14 MeVs coming off, 14.1 MeVs of neutrons. They just stream and hit the wall. But then you also have alpha particles, which are coming off.
So what's the conversion of the
About 3.5.
What's the conversion of that?
I'm assuming 100% conversion. But you know, if you had a steam cycle, it would be 30%, or as close, you could get close to 50%. All right, so progress towards fusion. I want to say a little bit about that. So on the x-axis is temperature, and the y-axis is the triple product, which is density of the fuel times the temperature times the energy confinement time. These are both important metrics in fusion. Temperature, it's very hard to get the plasma up to high temperature, so that's important. You got to get around 10 keV to get fusion to work. The y-axis, so there's a Lawson criteria, which is balancing the fusion power out with the losses, confinement losses. And if you do that and you assume 10 keV, you get the Lawson criteria, which gives a limit on the density times energy confinement time. So you take the Lawson variable, n times tau e, and multiply by temperature, and you get the triple product. So that having a high Lawson number here isn't close to fusion necessarily. A solid material would have a high Lawson number, but it wouldn't be a 10 keV. So by multiplying by temperature, you get a good metric. So what I want to show here, this is a busy, messy plot, and it's published recently. Actually, and Sam is one of Tobin's previous students. They're now at DOE, ARPA-E, these two folks, but this one was a student at CU, grad student. Is the Tokamaks here. JT60 is Japan's Tokamak. TFTR is a shutdown US Tokamak. D3D is the operating US Tokamak. JET is a shutdown, very recently shut down European Tokamak in Colloquium. NIF, we've already talked about. Omega is the Rochester. So we have some Rochester laser. So we have we have the laser ICF results. We have the Tokamak results. Here's the NIF result that we just talked about. Here's ITER and Spark. Spark is the Tokamak that Commonwealth Fusion is hoping to bring online in 2025. ITER is the International Thermonuclear Engineering Reactor being built in Cadarache, France. It's supposed to finish in 2025. They're saying 2029 now, but they're keeping their schedule, or they say that they will do DT operation by 2035. You know, again, fusion is always 30, maybe fusion is always 10 years away now. I don't know, but
how high off the graph is commercially viable?
up here at 10 or so. So,
Okay. Right up there.
so we're ITER. ITER's going to scientifically achieve what's needed for a commercial reactor. It's not going to have a steam cycle, and those things. All right. What's interesting, another thing I want to point, there's a lot to tell you, but the FRCs here are the diamonds. Those are the private companies, the startup companies using the self-organized plasma, and they're quite lower. So they're not getting the triple products that the ICF or the Tokamaks are getting. All right. So I wanted to say, I guess I'm doing okay now on time. So I want to say a little bit about what these self-organized plasmas are that the companies are using. This FRC, field reverse configuration. What is that thing? And so we're going to geek out a little bit on plasma physics. I apologize, but if you these are both there's Spheramax and there's field reverse configurations. They're both categorized as what is called a compact toroid, and this is what a lot of the companies are using because it's really neat. It's self-confining. It's a vortex with a lot of helicity. You have a significant amount of magnetic field and plasma pressure, and it confines itself. So it's a remarkable little thing. So the idea behind these compact toroids is to set J cross B equals 0, which is the dominant force in the fluid. This is sort of a theory perspective. J cross B is like the Lorentz force, okay? So you set that to 0. You say it's a force-free configuration. And then J is parallel to B. Then you solve Ampere's law. And you can get, if you do this, you can get these helical vortices. They're just fancy plasma smoke rings, okay? They're smoke rings that are made of plasma. And the one way to create these is what's called a plasma gun or a Marshall gun, and you have a coaxial gun, and you puff a gas in it, and then you fire a capacitor bank so that there's a voltage between the inner conductor and the outer coaxial conductor. The gas breaks down, you get current through that plasma, and there's a magnetic field that's generated by the inner electrode. And so there's a J cross B force, J cross B going in here on this plasma. This is the momentum equation for a plasma, the MH, magnetohydrodynamic version of it. And it shoots out. and it goes off in a puff of smoke ring, okay? But it's a plasma smoke ring. And then you can heat it and you can manipulate it. This is a spheromac. And a spheromac will expand, but it will live. It will hang around for milliseconds, just like a smoke ring. It's self-confining. You can keep it from expanding if you put it in what's called a flux limiter, a can, conducting walls. You can fire this thing into a conducting cylinder, and then it will stop expanding. It'll just bump against the conducting walls and stop expanding. So this has been known for a long time. SSPX at Livermore, they were doing experiments when I was a graduate student, which is the Stone Ages. So this has been going on for a long time. You can generate these other ways. You can have an axial magnetic field, and you can switch the sign suddenly of the axial magnetic field, and then you get a self-organized structure, the FRC. And the difference between a spheromac and an FRC is simply not having a significant toroidal magnetic field or self-confining toroidal magnetic field. Then you're in the FRC regime. And but they're really very similar. And you can get FRC by merging two spheromacs. You can get it a variety of ways. So the problem is that it involves transients in voltages, capacitor banks, and material walls, and you pick up impurities. And so it's just very hard to get these FRCs hot. And experimentalists know this, but they're very appealing from, if you just explain it to somebody, it's like, oh, wow, you get self-confined plasma. But it's really hard to get them hot. And so when I hear somebody saying, I have a new fusion scheme, and there's a company in Longmont who's recently approached me, there's a company in Broomfield that's recently approached me, I say, how high temperature have you gotten? And typically, they haven't gotten very high temperature. And why is that? Because plasma will radiate like crazy as you heat it up. And so you know this from arc welding at atmospheric pressure levels, pressures. You can add an enormous amount of power to a plasma, partially ionized plasma, and it will just radiate, atomic radiation, line radiation, okay? Transition between states. And it's really hard to beat this. No matter how much power you put into the plasma, you get that much heat and light out from the plasma. And you have to protect yourself if you come near one of these plasmas because it's just radiating like crazy. And it's really hard to get past 150 eV or so because of this phenomena. And you might say, well, Scott, that's kind of that seems kind of high. And if you looked at just ionization of hydrogen, the ionization potential for hydrogen, you'd say, well, it wouldn't have to be quite that high. But these plasmas inevitably have impurities that are radiating. And what's shown here is the radiated power as a function of temperature for carbon. And it's very high at low temperatures, and it's just hard to get here. This is what's known as burn through. Eventually, if you get to high enough temperatures, everything becomes great. The radiation stops. The plasma becomes fully ionized. And then you could just heat it up. You could heat it up to 10 keV. But it's hard to get there. It's hard to get past this radiative barrier. And that's what's known as plasma burn through. And experimentalists know exactly for their particular device, they know exactly the operating procedure to start off to get there. Now there's a quick way to beat it, and that's just drop your density. But the Lawson criteria limits that says our density has to be pretty high in a fusion reactor. So you can't just lower the density. You have to do this burn through for a plasma that has a high density. Okay. So that's one limiting factor. If you're a startup company, you got to get past the burn through issue. And the Spheromac at Livermore had a heck of a time in the 90s getting their plasma up to 200 EV. Another important thing, I want to talk a little bit about fusion power scaling. And to do so, I have to tell you a little bit more about plasma physics. So there's something called the plasma beta, which is the plasma pressure divided by the magnetic pressure. And you might say, oh, well, okay, so what? Well, beta is very interesting, because if beta is small, the external fields are in control, and the plasma is well behaved. However, as beta gets a little higher, the plasma can start to generate currents and magnetic fields and disrupt or just blow up. These are macroscopic instabilities described well by using magnetohydrodynamics, the theory of conducting fluids. Coronal mass ejection is a great example. So, pressure builds up and density and temperature build up, and boom, there's a coronal mass ejection where the plasma can blow through the confining magnetic field. Same thing happens in a tokamak or any fusion device where you have magnetic confinement. So given your experimental configuration, the device you have, there is always a beta limit, and it can be calculated using computational linear analysis computationally, though, with an MHD calculation. And so beta is sort of set at some value for a given type of configuration. So if we, I'm having troubles here. So going back to the fusion power in watts, it's the density of the fuel, two fuels that are fusing, so n squared, times the cross-section of the fusion reaction, and this has to multiply by the weighted velocity of the two species of fuel, so there's an averaging of the Maxwellian distribution, and then you have the fusion energy times the volume. That's the fusion power in watts that you're going to get out. So you can rewrite this with that beta parameter, and you get the following. And beta is, again, going to be some maximum value that you just can't beat because you have a particular configuration, et cetera. The magnetic field isn't going to change the shape of the configuration. So if you rewrite it in terms of beta, assuming beta is constant, then you see this b to the fourth scaling of the fusion power. And that's huge. If you increase your B field, you get an enormous gain in fusion power. And this is what MIT and Commonwealth Fusion are banking on with their design. It's an old idea, but the new technology is the high temperature superconductors that can run at 12 Tesla. But one thing to learn here is that if you increase your B field, really good things happen. There's another parameter here, which is the sigma V over T squared, and that has to be that should be maximized to get high fusion power, and that's why you want to get up to 10 keV for deuterium tritium. But that brings up another topic, which is our alternative fuels. So the startup companies these are green tech companies. They don't want neutrons, because neutrons, they damage the wall, and they generate low-level radiation. So you don't want to talk about neutrons if you're trying to raise venture capital. And so you talk about alternative fuels because they sound really interesting. But if you look at what's going on here, the sigma V over T squared for these alternate fuels. So there's two popular ones, D-helium-3. Helium-3 doesn't exist on Earth. You have to go to the moon to mine it, or you have to generate it using some nuclear process. So, but anyway, if you had the stuff, you could do the D-helium-3 reaction that produces a proton and an alpha particle, but it's down by a factor of 50 in the sigma V over T squared. That means your fusion power is going to drop by 50. Not only that, you have to go up by a factor of 5 in temperature. And it's really hard to heat a plasma. So we're talking, we can't get to 10 keV. Well, maybe we can, but we're trying. But we're not going to get to 58 keV anytime soon. But nonetheless, this is Helium Energy's proposed fuel. TE is proposing proton boron 11 that produces 3 alpha particles. Okay, this is a factor of 10 or 100 difference in sigma v squared and factor of 10 difference in temperature. Just no way in my lifetime. So DT will be the preferred fuel for the first fusion reactors. Okay. So with the little time I have left, I want to tell you a little bit about what a tokamak is. You've all heard about tokamaks. These are the best performing fusion reactors. And this is what Commonwealth Fusion is proposing with a 12 Tesla field. ITER has a 5 Tesla field, uses conventional superconducting magnets. So particles spiral on field lines, and so if you have a strong toroidal magnetic field, you'd think you could confine the plasma. This is just a toroid from E&M from 3310. You'd think you could confine particles quite well, but actually you can't, because there are drifts. There's slow drift motion that cause the ions and electrons to separate, and so you have to add a poloidal field. And the way you do that is by adding a toroidal current, which then generates a poloidal field. Okay, and so that's the tokamak, invented by the Russians in the 50s. So so the plasma, so you generate this plasma current using a transformer circuit. You ramp up a current going into the primary winding, and the plasma behaves like a secondary winding and generates a current. Okay, so now you have a toroidal field and a poloidal field. You have a helical field, and that provides good confinement. So let's just go back to the purely toroidal field. So in plasma physics, there's a curvature and grad B drifts. I won't tell you where these come from. But the key is that there's a sign here. Okay, so if we work through grad B, you have Ampere's law. Your toroidal field coils are here. You can draw Ampere's circuit here, or whatever you call it, loop, and then you get 1 over R. So the B field increases as you go in. You can't beat that. You can't violate Ampere's law. So then the curvature and grad B drifts cause, in this configuration with the B field into the board, cause the ions to go up, the electrons to go down. That produces a charge separation, an electric field, and then there's another drift in plasma physics, the E cross B drift, which would be radially outward given this situation. And you can flip. You can't change the direction of grad B, but you can flip the sign of B in the torus. You'll have the electrons will go up and ions will go down. That's all. But you have the same phenomena. So that poloidal field fixes things. That poloidal field causes the motion of the particles to be helical around the tokamak. Okay, they spiral around. And here's a projection of that helical motion going around the tokamak. And what happens is those drifts for an ion, the way I showed it, are up. So it goes up, it goes to a helix that's further out. But then as it goes down here, it goes up too, and then it goes to a helix that's further in. And the net effect is that the drift motion cancels, and you get closed orbits. And you could show this if you take the magnetic field for a tokamak and you solve mechanics, you use adiabatic invariants. You can show that these orbits are indeed closed. They have very interesting shapes. They're not all circular. Some are shaped like bananas. They're called banana orbits. Okay, so that's the idea behind a tokamak. Now, just briefly, I want to talk a little bit about what's going on at Colorado. So one of the key challenges is energy transport. Now, if you study, there's always turbulence. It's always going to be there. So if you study turbulence, you're guaranteed job security because there will always be a problem. So this is one of those situations. You have large density and density gradients, and they drive instabilities that saturate at very low levels, a fraction of percent in the density fluctuations and the electrostatic potential fluctuations. And these drive, you get a broadband turbulent fluctuations, and this causes the particles to diffuse, not surprisingly, but it's actually the E cross B drift, which enables the heat to get out of the center of the tokamak. And so we study this using gyrokinetic simulations. We have kinetic ions, kinetic electrons, electromagnetic. We have a big code. We run other people's codes. It's a very interesting problem. We do a lot of reduce models. We even reduce the kinetic theory, so our kinetic theory is simplified. That's we average over the cyclotron motion. That's the gyrokinetic part of kinetic. Okay, but it sounds really confusing and hard to understand. Only specialists know what's going on, but you can think of it as Rayleigh-Benard convection. Okay, that's basically, we study the fusion version of that, or the tokamak version of that. So in Rayleigh-Benard convection, you have a cold ceiling and a hot floor, and this generates convective cells, Rayleigh-Benard convective cells. And if you have more of a temperature gradient between the top and the bottom, then you drive a turbulent convection, which is beginning to set up in this recent paper on Rayleigh-Benard convection. So we have a similar situation. We have a strong temperature gradient. We're always turbulent, and in this case, it's the buoyancy. In Rayleigh-Benard convection, it's the buoyancy force, or the gravity. In the tokamak problem, it's the curvature and the grad B effects that play the role of gravity. Gravity is way too small to be of importance. So that's what we do in a nutshell. And I think I will stop. Oh, I'll go to my conclusion, just because you've been a great audience, and so I'll end on time. So fusion has the potential to produce clean, zero carbon energy. Hopefully, I've convinced you of that. There's been a lot of recent investment in fusion energy on the order of $6 billion. That's the Fusion Industry Association's estimate. NIF results show ignition is possible now in the laboratory. That's very exciting. I discussed important scaling of B to the force. So the magnetic field is critical. If we can increase it, we can get more fusion power. The advanced fuels are too futuristic at this point, and so DT has to come first. Tokamaks are the highest performing fusion reactors near term, and depending on who gives the talk, you might get a different view on that, but I think it's pretty clear that tokamaks perform much better than the other types of devices. Other confinement schemes need to demonstrate the high density temperatures and longer confinement times. So the TAE experiment actually did have pretty high temperature, but it had very short confinement times. It has to be bigger than a millisecond. I mean, tokamak has confinement times of a second. Of course, it depends on the size of the device and other things, but these are still very short confinement times. And then the turbulence limits the confinement, and that's what we do. Okay, well, thank you very much.
Thanks, Scott. Very interesting stuff. So no questions. So I'll just go in the order I see them back there.
Most of the energy release is in the form of neutrons. And neutrons do not couple well to the grid. So they activate all the surroundings. So what solution do you have to that?
Yeah, this 14 MeV neutron, and only Jerry's bringing up the fact that only 3.5 MeVs come off as alpha particles, and then Yeah, so you have to absorb them. You need to breed tritium. So there's a real issue of where is all this tritium going to come from? And so you have lithium walls, and then the tritium interacts with the lithium to breed tritium. The neutrons. The neutrons hit the lithium atoms and breed tritium. So you'll have a liquid or solid lithium. It could be a compound, a chemical that has lithium in it, like Commonwealth Fusion is proposing a solid. ITER will eventually have a test cell that will be a liquid lithium first wall, where the neutrals will be absorbed by lithium. So that's but it is an issue. I mean, 14 MeV neutrons damage stainless steel, right? But there's a lot of material challenges, like how long will the wall last? How long will the structure last? In a fission reactor, you have zircaloy. So there are various alloys that are do very well under extreme neutron, in an extreme neutron environment.
But the energy of the neutrons is so much higher, they're hard to stop.
Yeah, lithium, collide with lithium's light, so it'll heat up, and then you'll have energy exchange. You'll have a heat exchanger.
Currently, we get tritium, hydrogen-3, by pumping on nuclear weapons.
We get tritium from heavy reactors in the CANDU reactors in Canada. There's also a reactor in Wilkes-Barre in Tennessee, which produces tritium. So the U.S. has their own, but really we rely on Canada. That's mainly the main source.
Question done. Oh,
E in ITER stands for experiment.
Yeah, it used to stand for engineering.
question there.
So one of the criticisms of ITER is it's so massive and expensive. Going to these high peak fields, how small can you make a Tokamak? Virtually viable.
The spark reactor, this is Commonwealth Fusion's reactor, has a minor radius of like 0.6, 0.57 meters, and a major radius of 3 times that. So it's smaller. It's down by a factor of 3 in size. But things go cubed the linear dimension in terms of cost. So I was told once, I'm not an experimentalist, but I was told once that you just take the price of the experiment is basically you just take the volume of the stainless steel, and so it scales as cubed.
But spark is the size of current experiments.
Yeah. Dimensional size, yeah, it's the size of present day smaller tokamaks, but it's got a 12 Tesla field, so in effect, it's from a theorist perspective, it's much bigger in terms of cyclotron radius.
So Marcus, saw you had in.
The monophysics that venture capitalists typically invest in 10 concepts.
Yeah.
And over a time scale of 10 years, 9 fail.
Yeah, exactly.
Champion has to fail.
Right.
So the main advancements you showed are all in the similar concept that you all suffer the same challenge with getting temperature.
Oh, there's all sorts of different devices.
But it's different.
These are really different.
So,
Yeah.
So who or how is the narrative that this will pay off on a typical temperature?
Well, you hit it on the head. Back in the olden days, which was 2021, you could get free money, if you had an idea, because they had the probability of payoff was very low. They still take you on, and that's great. That's a great way to do science. You get all this funding. That's what's going on. But one thing you said that was incorrect, Marcus. I think there's a wide range of different types of experiments, and there's 40 or so companies. I just touched the surface. So there's a lot of different.
But it was the magic.
See, Eric has a question. Are there any student questions? No students. Let's go to Eric next then.
So I was talking to a guy who was interested in sort of about nuclear fusion a lot. saying, even if you could solve this problem in a small cross section for that process, the helion process that releases the three alpha particles, that's what's called.
Yeah, boron 11 and proton.
You're saying like neutrons get a bad rap because say you had 3 gigawatts of thermal power in alpha particles coming and getting absorbed. They have a very short cross section. We're getting very short absorption of that to your surface. 3 gigawatts of power to your surface, you're going to like vaporize your surface. The fact that the neutrons punch in is actually a feature.
That's true.
Larger volume if you want to actually somehow extract that into a steam jet. So that was his story.
Yeah, that's a good point. And in fact, power handling is a serious issue. You have just the 3.5 MeV. ITER is going to have 100 megawatts of plasma power coming off of it, and it's got to be absorbed at what's called a diverter plate, a tungsten plate, and it's going to be like 20 megawatts, 20 megawatts per meter squared heat flux. That's really tough, and that's a real problem. You're right. The neutrons help because we don't have to absorb all that energy right at the plasma boundary interface. Exactly. I should have said that. Thank you.
I saw a question over there. Did you guys still have a question? Yeah.
Yeah, I was sort of confused about the derivation for the scaling power with the field to the fourth.
Yeah.
You showed it as proportional to beta squared, and beta was proportional to maybe some slide 19 or something. It seems like the term cancels out here. Oh.
Yeah, you're right. Beta has B squared in it, so it looks like a swindle, right? And that's legitimate, but beta is some maximum value.